Swayam Prabha. Digital India. Educated India.
Right? If you see here, you could probably notice that in the polygon case, you have the medial axis that sort of passes through in the middle, but then there are certain other spokes that are piercing through the object. The medial axis will not pierce through the object, right? So that's why we said you could approximate the medial axis with a Voronoi diagram, and there are many algorithms to do that in a discrete setting, right? So we studied a lot of things today and even yesterday. I thought I'd have one slide to sort of connect the dots. These are all somewhat related to each other, especially the sign distance field that we looked at yesterday in the implicit setting, the medial axis, the Voronoi diagram, right? So this slide sort of summarizes what we have here. So you have shape. At one hand, the shape is the boundary of a solid, and you have its medial axis, and it's the SDF of the shape, right? The shape and the medial axis are related. I could solve the Eiffel equation or explicitly compute the SDF. That's going to derive the SDF from its shape. Or if I want to go back, I can take a zero level set of the SDF and recover the shape. On the other hand, I have the medial axis, and I can compute the medial axis, or at least approximate the medial axis using the Voronoi diagram. There are, of course, other techniques to calculate the medial axis as well. For example, the maximal ball is the basic definition of a medial axis. And with the medial axis, so medial axis is a reduced representation of a surface. As you can see, it's a one-dimensional. It is one dimension less than the original dimension of the shape. So if I store the radius of the maximal ball at every point on the medial axis, I can recover the shape with the reconstruction. So I have to take a union of all those balls, and I can get the surface back. Then the SDF and the medial axis are also related. The medial axis can be computed by taking a local maxima of the SDF. So remember, we talked about it yesterday, that you notice the blue regions in this SDF, and the highest values in this mountain of sign distance field corresponds to the medial axis, and that is exactly the locus of the local maxima. So you connect the highest point of this mountain, and that is precisely the medial axis, right? And you can, of course, construct the SDF given its medial axis. Again, you need to know the ball radius, and that would help you recover its SDF. So in a sense, these three representations, the explicit shape, its medial axis or Voronoi diagram, and the SDF are related. And we also know that the Voronoi diagram and the Delaunay triangulation are also related because they are dual of each other, right? So I hope all of this makes a little bit of a sense now. And that's very much about Voronoi diagram that I wanted to talk. So I think we have now the next topic of surface reconstruction, which is the last topic for today. But any questions till now on Voronoi diagram or Delaunay triangulation, or in general?
So like we have discussed Voronoi diagrams, say for 2D shapes, we'll also have for 3D and other dimensions like that.
Yes,
they can be.
Yes, you can define Voronoi diagram. Yeah. In that case, Voronoi diagram will have polyhedrons. Voronoi regions would be polyhedrons.
Okay.
In 3D, for example. And if you have, for points, it is polyhedra. And then if you have 3D lines or planes, between plane and a line, it would be a paraboloid. And then you can have those curved surfaces, a collection of curved and planar patches.
So like just it is identical to how we analyze for 2D.
Sorry.
Sort of identical, or you can say similar to how
Yeah,
we
yeah.
did for 2D, as in no real
Yes, yes, yes.
change in
The
analysis.
concepts are similar. Yeah, the concepts are similar, and it is defined, usually defined for n-dimensional space. There's a very nice book by Okabe et al. Um, if you are interested in Voronoi diagrams, that gives you an excellent background on Voronoi diagrams.
So can you please write the name?
I think. Oh, okay. So that one I don't have it in the references, but I can add that. But if I were to just let me write. I don't quite remember the name of the book, but I know the author's name. It is Okabe. It is a book by Okabe. Okabe et al. So if you search Okabe, you will get that book's name. But I'll add later on. I'll add that to the slides as well.
Thank you.
All right. Okay. So let's come to the last topic for today, which is surface reconstruction, and this is an interesting topic because you have usually if you capture data from the real world, and let me come back to what I discussed yesterday at the start, is we usually want to represent geometry digitally and then also reconstruct the shape, and we usually have to capture data from the real world because that makes more sense, right? I mean, we want to analyze real world data. So when you capture data through various sensors, there are different artifacts in that data, and some of these are, you may have non-uniform sampling density. So if you look at this signal, which is, you can think of a shape maybe. The sample points are denoted as dots. These dots may be non-uniformly sampled, and that poses a problem because what I get is dots. So I have to connect these dots to make a shape. If there are larger gaps in the data, the sampling density is not uniform, then it becomes very difficult to see which dots are connected to which other dots. There may not be a clear-cut topology, connectivity information between the dots. Add to it that there could be noise in the data set. The points may not exactly lie on the surface because these sensors have their own limits. Some of the sensors will not work great in low lighting conditions, right? They may be more accurate at some points and less accurate at other points. So there are different, limits of these sensors. Then there may be outliers. There may be outliers in the data. So points that do not really belong to the surface, but are still captured because of errors, because of sensor errors, or some temporal incoherence in the lighting conditions or anything else. Then there could be misaligned scans, because usually if it's a bigger object, you would want to scan it from multiple sides and merge those scans. That is, you capture points, you capture points from one side, and then you capture from another side, and then another side, and then you would want to merge them, align them together. And this alignment can cause problems because sometimes this alignment may not be perfect, and these misaligned scans will then result in overlapping points that may be somewhat, they may have a gap in between. Then there could be missing data. For example, there could be occlusions. So if I'm scanning something, there could be some occlusions that prevented me from scanning part of the shape. So these are all problems with data captured through various sensors. So this overarching problem of surface reconstruction tries to solve some of these problems. And surface reconstruction has come a long way. today we are also looking at, deep learning based surface reconstruction, because that look, certain shapes should be like, like in a certain way. So maybe there is some learning that can happen in reconstructing a shape. But classically, there are purely geometric based reconstructions that have been used, and there are certain very, very nice, very well known algorithms. And we will discuss two of the algorithms today. And if time permits, I might, go through maybe a couple more. So usually the input for a surface reconstruction could be a set of points or cross sections, a defective mesh. And what I mean by a defective mesh is that, let's say, part of the mesh missing data, missing triangles from the mesh, or noisy data in the mesh, noisy mesh, or it could be depth maps. Is anybody familiar with depth maps here? What are depth maps? Or RGBD images? Anybody knows what are depth maps? I can bet that some of you own sensors to capture depth maps without knowing that you have such a powerful sensor in your hand. You might as well be looking at it right now. A lot of cell phones today come with depth sensors, especially the new ones. If you have like 3, 4, 5, 6 cameras in your phone, no, I'm not talking about LiDAR. Yeah, LiDAR is like a more expensive side of, point capturing device, but LiDAR is not depth maps. The Kinect is a depth map. Yes, Abhishek. A Kinect is a depth capturing device, but again, Kinect is bulky. Today, the depth capturing devices are part of your mobile phones. If you notice, if you have a newer phone, and you may notice that you may have a depth camera in your phone, and if you have a depth camera, then your camera is essentially capable of capturing a depth map of the scene. A depth map is basically just like an image, a photograph, but instead of capturing colors for every pixel, it captures the depth, could be in meters, the depth from the camera center to the subject. Right? So for example, if you're photographing a table, then the depth map would be the image of the table with every pixel storing the depth from the camera to that point in the table projected from that pixel. So you connect a line, a ray going from the camera center, connecting that pixel and out onto the table. Wherever it intersects the table, that distance from the camera to the table is stored at that pixel. That is a depth map. Okay, and usually these cameras also have, you probably all of you will have a RGB camera. So together we call it an RGBD image. RGB, then red, green, blue, and D for depth. So there are with the advent of Kinect, Microsoft Kinect, there have been a lot of focus on how could you use the Kinect to construct the 3D scene by stitching different depth maps together and coloring them with the color image. Okay. Okay. So so that's one. The output of such a surface reconstruction is usually a mesh. So we are mostly interested in creating a mesh out of points, and of course also colorizing them. I can also briefly discuss the multi-view stereo if some of you are interested in discussing what is multi-view stereo algorithm. I can give an overview of such an algorithm if time permits. So The output could be a mesh, a parametric surface. In some cases, I might have point data, and I might want to fit, a CAD surface. For example, I want to have, planar sections from a building scan. Let's say I might want to fit a CAD surface to it, or a parametric surface, perhaps, which gives me more, smoother surfaces. But a mesh is usually what I want at the end of the day, usually, right? So that's the output. So two algorithms we are going to discuss today. The first one is the RBF reconstruction. RBF stands for radial basis functions. And let me so then if I can change that's fine. So an RBF reconstruction is a global gives you a globally smooth surface, and you have globally supported basis functions. Phi x equals to phi x equals to x here, for example, and mod of x. And basically, given a point, you have given a point cloud pi, you want to construct an implicit function F. So most of these algorithms work with implicit functions, and we have already discussed implicit functions yesterday. So you will find that implicit functions find a great application when it comes to surface reconstruction. A lot of algorithms use implicits because implicits are very powerful. Maybe we didn't discuss yesterday, but implicit functions very well handle the topology of the underlying surface. Changes in topology are very well captured in implicits. So this is the form of an RBF implicit function, and this is what we want to recover. Okay, so we are given a set of points pi, and this is my objective, you could say. Objective in a sense that the final function that I want to represent my surface. And remember, you could think of this to be similar to sine distance function, but the values are not distances here. The values are some numbers, but I'm interested in the zero level set here. So while the distances are not the values are not distances, the zero level set represents the surface that I'm interested in. So from points, I want to go to this implicit function and then take its zero level set, and done. By the way, today's lab is going to be interesting. We will go through some of these concepts in Python and using libIGL. So anyway, so fx is a polynomial px plus a combination of RBF functions defined over defined around each point pi. Okay, so I think some abuse of some notational differences here. I think this point cloud pi should be xi. Yeah, I'll fix that. But this pi, please read it as xi because in the expression below, I think I made a typological error here. So you have lambda. The unknowns here are the parameter coefficients of the polynomial, and px is just a polynomial. It could be a linear polynomial, or I think it's most likely a linear polynomial in this case. So c1x plus c2y plus c3z plus c4. So you have 4 coefficients of this polynomial, and then you have this radial basis function phi, which is defined around xi. So you take at point x, you take the distance from x and xi, and then the radial basis function is going to give you the magnitude of this vector. The unknowns are the coefficient c and then lambda i's, because you need to weight. It's a weighted combination. It's a weighted combination of these radial basis functions. The lambda i's are unknowns and the c's are unknowns. And because you're going to be taking a level set 0, so remember that for every point p, we want an interpolating surface, right? We want a surface that passes through that point. And if I'm interested in the 0 level set of this implicit function, then that says that every point pi is sitting on this level set what would be the value of at these points? The function values would be exactly 0 because these points are sitting on the level set, and any point on the level set 0 will have a value of 0. So, but that leads to a problem because if if f of pi is 0, then f of pi is 0, then in that case I have a trivial solution and it doesn't work out. So I need to then what I do is that I take certain points in the positive direction and certain points in the negative direction of these points pi. And usually in these point reconstruction problems, I not only have the point but also a normal vector associated with each point. So basically I know what is my surface orientation. And this is true for many sensors, especially if you do a RGBD reconstruction. You know what is the normal vector because you are mostly capturing from the outside, or there could be other clues that could tell you what is the normal vector at each point. So it is okay to assume that every point comes with its normal vector, and then with RBF, what you do is that you just nudge that point pi in the positive. So basically you say pi plus epsilon times normal vector and pi minus epsilon times normal vector. So basically I'm moving a little bit epsilon distance above and below that point along the normal direction, and I get 2 points, one positive, one negative, right? So I could then say that I moved epsilon distance, so I could say that my fx is epsilon in that case, and then that would help me solve this problem, because if I just have the 0 points, I'll not be able to solve it because the constraints will result in a trivial solution fx equals to 0 and the system will collapse. So that's the system of linear equations that I get from RBF formulation. I have the matrix that consists of phi and the polynomial p with unknowns lambdas and the coefficient c appearing in the vector, which is equal to the function value f, which in this case would be whatever distances you moved along the normal direction. You need not move all the points epsilon. You could move epsilon 1, epsilon 2, whatever you want, but that epsilon will come here. Whatever is that function value you think will come here, and for the polynomials you have 0 in that row. So you have this linear system of equations that you can solve, and let's take a look at some of the results. So let's say we have this bunny mesh, and for now let's ignore the mesh and only consider the points. You have this linear RBF where the RBF function was a linear function of phi r equals to r. You could change the RBF function to be a cubic. In that case, you get a smoother surface, but there is some shrinkage of the bunny. You could regularize the cubic RBF, and that gives a better appearance. But RBFs is an old method, and it was very well known earlier, which was later replaced by another method, which we can look at now. But anybody has any questions on the RBF, we can quickly take a look at that. All right. So that was RBF, and then came the Poisson reconstruction method. That's a very it's a very interesting method again, and Poisson reconstruction tries to recover the shape from a set of oriented points. So again, every point has a direction, a normal vector associated with it, and essentially, you want to recover the shape using, you solve for the indicator function. So what is an indicator function of a shape? The indicator function of a shape says that if a point P is inside the shape, its indicator function is 1. If it is not inside, then indicator function is 0, right? So basically, you want to recover its indicator function. And if you do that, you have recovered the shape of the object. So let's see how it is done. So essentially, if you're given a sorry for that, I'm trying to minimize one window here. Right. Anyway, so if you're given n gradient data parts, that is a point and its gradient, that is its normal, you want to find out a function f such that the gradient of the function at the given data point is the given gradient. So grad f of xi equals to gi. This is what you want to satisfy, right? You are given xi and gi. Xi is a point and gi is the normal vector or the gradient at that point. So you want to recover a function f such that the gradient of f at xi equals to gi, right? And we hope that while doing so, we will have we will define a surface that will also work out for points other than xi. Remember, xi are just a set of points, a discrete set of points. So what we could do is we could solve the normal equations by taking the gradient of the above equation. We say that the gradient of f equals to the gradient of gi. But let's take a look at an observation, is that the normal field n, remember we are given the normals n or the gi values. The normal is gradient of the smoothed indicator function, right? So the indicator function has a discontinuity. The indicator function is c minus 1, because look what happens at the boundary. At the boundary, inside the boundary I have 1, and outside the boundary I have 0. So there's a sudden jump, and that's a c minus 1 continuity, or in other words, a discontinuity, a positional discontinuity. So we can assume that the given normals are sampled from the smoothed version of the indicator function. And you can imagine that a smoothed version of an indicator function is something that gradually goes from 0 to 1 rather than a step, right? So you have a smooth function that smoothly transforms from 0 to 1 at the boundary, so that the normal is smooth. Because if you have an indicator function, the normals would be difficult to define. So let's call this smoothed version of indicator function as the x hat s, where s is the surface we want to recover. So then instead of solving the equation above, I solve the equation. I want to recover the smoothed version of the indicator function. So gradient of xs equals to n is what I want to solve, and I solve it using the Poisson equation for xs, right? So grad square xs is grad dot n, where n is the set of given normals, right? There are certain implementation details which I have skipped here. There's a very well-known paper by Kazdan et al. It's maybe in 90s, published in 90s, but that gives all the necessary details. Essentially, you solve this Poisson equation on an adaptive grid in 3D, for example, an octree-like grid, and you do a solution, an accurate solution only along the boundary. And these are some of the outputs of a Poisson reconstruction. So basically, you have this point cloud, and then you recover a triangle mesh. How do I recover a triangle mesh here? So when I solve it, let's say I solve it on a uniform grid, a volumetric grid, and at every point in the volumetric grid, I compute an implicit function value f. So you see that when I solve this Poisson equation, I solve it on a domain, on a volumetric domain. So I have a grid, and then for every grid point, I calculate, I solve this Poisson equation. And then once I have that grid solved, I take a zero level set using marching cubes. We discussed marching cubes yesterday, right? So the marching cubes will then give me a triangle mesh. So the triangle mesh is from marching cubes. Okay, so that's Poisson reconstruction. There are many more reconstruction algorithms, and I could have included more, but I believe I just wanted to sample, two prominent algorithms, and there are many more algorithms for reconstruction, but these are some samples. So these are some of the references pointing to some of these algorithms. For example, the last one is by Kazan et al., which is one of the papers. Okay, it's 2006, not 90. It's even recent. So Poisson surface reconstruction. Anyway, questions. We are done for today, but I can stay back for some minutes and we can take questions here. And if you want, I can discuss something else, or if maybe we can take questions if people want questions.
So just one quick question.
Yes.
Hello. Yeah. So in the RBF
yes,
reconstruction, polynomial is added as a regularization, basically, or something that smooths the surface, or
right.
something that avoids overfitting.
So polygon is to add smoothness. If I'm not wrong, it's used to add smoothness. What happens sometimes is there is an additional regularization that is added to phi here. The last one, I haven't included the regularization equation here, but that is, so in the same equation, if I add another term that says plus k times lambda I, that adds a regularizer to it, because this system of equation, if you can't solve it, then that becomes a problem numerically if you can't solve it. So, but pi, I believe, is only to make the surface smoother.
Okay. And sorry, one last question from my side.
Yes.
So
sure.
Here the estimates of normal also can be noisy, right? In both these algorithms, you do need an estimate of the normal.
Yeah, that's true. Because you can't trust these sensors. So these normal estimates can be noisy. So in many algorithms, we do smooth out the normals before we plug them into these, because you're right. The noise noise could be present both in the position and the normal. So for example, when you calculate these depth images are noisy in the periphery of the image. And also if you move back, if you move forward, the further away you are from the sensor, the more noisy they are. So if you have a wall that extends in the z direction, the estimate of points further away would be very noisy. In fact, noisy to the extent that you can't use it. So the most accurate estimates of point position is using laser sensors, LiDAR sensors.
Right. Thank you. Participants, questions?
Questions, I believe. Anything that wasn't clear, there are a few minutes. I don't think I could start a new topic because that would go over time. But let's stick to questions now. But of course, I can point you to different methods that you can look at. For example, there is an increasing body of work. So there was an algorithm called Kinect Fusion. If some of you have worked with Kinect sensor, there have been a body of research as to how to reconstruct a static scene by taking a lot of depth images from the Kinect sensor. So you take the Kinect sensor in your hand and move around into the scene, and then the Kinect Fusion algorithm will fuse all the depth maps and the color images, photographs, into a single scene live in real time and reconstruct the entire 3D scene. So that is known as Kinect Fusion, and it uses a modified version of distance field, all known as TSDF. It's called a truncated signed distance field. Truncated signed distance field, TSDF. And the modification is very simple. It says that we want a narrow band distance field because so what is meant by narrow band is that around the zero level set, you don't want to go further away. Let's say you want only the relevant distances are 10 centimeters from the zero level set, because you expect that whatever changes happens in the surface happen within that 10 centimeter range. So you truncate the distance field up to 10 centimeters, and you don't really care what happens beyond plus 10 centimeter and above 10 centimeter and below 10 centimeters. So you don't really care what it is. So it's a truncated signed distance field. The distance values are correct only up to plus minus 10 centimeter, and 10 centimeters is just a example here. Okay, so you use TSDFs for real-time update of these depth frames. So you accumulate all the depth frames in a single very large TSDF function, and then you do you calculate a mesh at the end of the day. So that's a Kinect Fusion algorithm. And then, well, I haven't explained any algorithm here, but that's the idea behind a Kinect Fusion. If you are interested what's happening in research in this area, the interest nowadays is on dynamic reconstruction. That is, how do I capture and represent moving objects? So for example, a dancer, how can I capture the real-time 4-dimensional performance of a dancer, given that I have some sensors around, maybe cameras or multiple depth sensors? How do I fuse, store, transmit, and display a 4D performance? And this is also known as volumetric video capture. You can take a look at that. And some of the algorithms that came up in the last 3-4 years, one of the fundamental algorithms in that was called dynamic fusion, which was based on Kinect Fusion. So Kinect Fusion is static, and dynamic fusion is the dynamic version of Kinect Fusion. And then there have been various improvements on the dynamic fusion algorithm. Okay, so I think with that, I will stop. It's already noon. More questions, please ask me. I can stay back for a few minutes. Otherwise, I think we can call it a day.